All right, so we've just looked at adding HBr, HCl, these concentrated acids to our alcohols, and we noted that's all fine and dandy, but problem here, we get the rearrangement. Note the last two examples, we had rearrangements. What if you don't want the rearrangement? What if you have this reactant right here and you don't want this product, you want the bromine over on this carbon. You want this OH to come off and you want the bromine to go right where it was. How can we do that? The answer is we can't using HBr. We note HBr, HCl, H2SO4, very general reagents. We've seen these all the time. We use them all the time. If you need a reaction to go the way a general reagent won't let it go, then you need a specific reagent. We've already had an example of that in the last video, SOCl2 and pyridine, a very specific reagent. It has a job, one job only. SOCl3 and pyridine, one job only. To dehydrate an alcohol via E2, so no carbocation rearrangement. We have two other reagents that will, instead of dehydrating the alcohol, will put the halogen where the OH was, put a halogen here, and those two reagents are SOCl2 and PBr3. Technically SOCl2 also needs pyridine. But SOCl2, thionyl chloride, converts primary and secondary alcohols into alkyl chlorides via SN2. PBr3, phosphorus tribromide, converts primary and secondary alcohols into alkyl bromides via SN2. So these are nice reagents because you just throw them in and you get your product. Nope, I'm not worried about the mechanism. These are specific reagents. They have a specific job to do. Can convert OH into the alkyl halide via SN2. Some people might ask at this point, okay, but what if you have a tertiary alcohol? Well, if you have a tertiary alcohol and you want to make a alkyl bromide, just throw in HBr. The carbocation's already tertiary. Much less chance you'll get any rearrangements happening if you're starting with a tertiary carbocation. So, here are two examples. It's very straightforward. Cyclohexanol, throw in SOCl2 and pyridine, put a chlorine where the OH is. Put in PBr3 instead, put a bromine where that is. All right. And note, for an example down here, if we start with this guy here, we have the secondary alcohol. Recall if we had an HBr, we would get the rearrangement, and so instead of putting the bromine on this carbon, this hydrogen would move over, and the secondary carbocation would become a tertiary carbocation over here. The bromine would go here. Put PBr3, the bromine goes where we want it. HBr, the OH comes off, secondary carbocation rearrangement, the bromine goes on the carbon that contains the two CH3s. PBr3, OH comes off, bromine goes where the OH was. Because it's SN2 reaction mechanism, no carbocations. Well, that's pretty nice right there. All right. So, starting with propanol here, 1-propanol, how would you make CH3CH2CH2CN? How would you substitute a CN minus for that OH minus? Well, let's go through our thinking here. First, we know CN minus from sodium cyanide or potassium cyanide is a really good nucleophile. So one might think, oh, just throw in some sodium cyanide. But then we're like, nope, that's not going to work because we have this OH here, and we know OH minus is a poor leaving group. So even though CN minus is a good nucleophile, it's not going to remove a poor leaving group. So we can't just throw in sodium cyanide. And so let's do this. What if we converted that OH into a good leaving group? Now, at this point, you might think, well, what if we just threw in some H2SO4? If we throw in some H2SO4, won't that protonate this guy? And that guy will leave if we throw in H2SO4? Yeah, it will, but recall that's going to give us an E1 or excuse me, since this is primary alcohol, that will give us an E2 elimination. We don't want that. So now we're saying, okay, throw in some HBr. If we threw in HBr, wouldn't that change this OH into a bromine? H will attach, or this oxygen will attack the hydrogen, become a good leaving group. SN2 reaction, the bromine will come in. Wouldn't that make this a good Br, a good leaving group, and make this down here? And then we could just have cyanide attack that? Well, that could work, except for one big issue. If you throw in HBr, then we are under acidic conditions here. And if we're under acidic conditions and you throw in cyanide, then the potassium cyanide or sodium cyanide, the cyanide gets converted into cyanide gas, CN gas, and that will kill you real nicely and real quickly. So if you use HBr to do this reaction, to put the bromine on here and then put in your cyanide, then you're dying. You're dead. Unless you take super precautions, but why have to go through all these crazy precautions if you don't have to do that? And now some are saying, well, what if after you put the bromine on there, then you make it more basic? Well, if you make it more basic, then you've got OH minus in there that will just come back and run your reaction the other way. If you had this plus acid and you add base to get rid of your acid, that base will react with this guy and we'll go back to the start. So the best way to do this is to just take this OH and convert it to PBr3, or convert it to bromide with PBr3 here. Don't have to worry about acids or anything like that. And then throw in your potassium or sodium cyanide to get that product. All right. Whew, going on. Long chapter here. What if we have ethers and acids? All right, let's just see what's going to happen, get it in our head, and then we'll work it out. If you have an ether, ROR prime, prime just meaning that we have a different R group. This could be like a methyl and an ethyl or something along those lines. If you had two equivalents of strong acid, HBr or HI, you will make two alkyl halides. You will get this R prime bonded to the halogen, this R bonded to the halogen. No, we added two HXs. That gives us two hydrogens and this oxygen left over. That's water. What mechanism will this go through? Well, it goes through whatever mechanism is necessary to get the job done. If R or R prime is primary, it'll go through SN2. If it is secondary tertiary, it'll go through SN1. Let's take a look at the mechanism down here. What if we had this tert-butyl methyl ether right here? Well, if we had an HI, hydrogen iodide, or hydroiodic acid, first thing is this negative oxygen attacks the positive hydrogen right here to protonate this guy to give us this protonated beast. Now, this is a good leaving group. Just as H2O is a good leaving group, alcohols that have very similar pKa's to water are also good leaving groups. So now this alcohol, this primary alcohol, could plain old just leave and generate this tertiary carbocation. Now you might question, well then why doesn't this alcohol, the tert-butanol, just leave to generate a primary carbocation on this methyl? I think you've just answered your own question. Will you generate a methyl carbocation? How stable is that? It's not stable at all. Now you're thinking, oh, but what about SN2 mechanism and not go through the carbocation? Recall, in these reactions, primary things react much more slowly than secondary and tertiary. Our SN1 mechanism is just a faster mechanism than our SN2 mechanism under these conditions. So we will get this CH3OH as our leaving group, make this alcohol methanol, and we'll generate this carbocation. Our iodide could come in, attack that carbocation, and we get tert-butyl iodide right here. Note though, we've got this methanol, it's an alcohol, we have HI around, so if we have that second equivalent of HI come in, just like we've done before, a primary alcohol, strong acid HI, oxygen attacks a hydrogen, generate iodide, It makes this primary beast here a good leaving group, but it's not just going to leave on its own because this is a methyl group. Even it would be an even less stable carbocation than a primary, and so this iodide will come in via SN2, attack that carbon, kick off the water, and we get our CH3I plus our H2O. All right, let's end here, and we'll start with epoxides in the next video.